I'm going to introduce you the circular motion and other application of Newton's law. Before we get started, we have to review the circular motion. And we can see in picture A, a car moving in a circular path. We describe this motion, the circular motion. And if the car is moving on this path with constant speed, v, we call it uniform circular motion. Okay. Circle. Here is constant speed. Okay. And then with a constant speed, we may first calculate the acceleration vector in uniform circular motion is always perpendicular to the path. Okay, he described that acceleration or uniform circulation should always perpendicular to the path. Why? If that were not true, there would be a component of acceleration parallel to the path. Yeah, this. Parallel to the velocity vector. Such an acceleration component will lead to change in the speed of the particle along the path. This situation, however, is inconsistent with the CI of the situation. And in this situation, we may have other paths like this. Okay. And therefore, for uniform circulation motion, the acceleration vector can only have a component perpendicular to the path, which is toward the center of the circle. And then we can get a relationship between center acceleration, velocity, and r by similar triangle in the maze. Assume the car in times t1 is here, and car after a time, at time t2, the car is here. And the t1 corresponding to r1 and r initial and v initial. This. And in t2, it corresponding to the r final and v final. And in figure C, is the triangle in figure C is come from here. As a result, we can see they are similar triangle. So the ratio of delta V over V is equal to delta R over R, because they are similar triangle. And then if we want to get a center acceleration, which is delta V over T, we can get from equation 1 here, because we just need to do this, and which is equal to V delta R over delta T. Yeah. And then if we do some math here is V, and then we can get center acceleration equal to V squared over R. Here is the relationship between center acceleration, velocity, and R. Also, if we describe the uniform circular motion in time, it's very convenient to describe by period t, which is the time the object need to finish a circle. As a result, the object with velocity v and the length of his path is 2 pi r. As a result, we get purity is equal to 2 pi r over v. Here, then we define the omega. Omega is the change ratio of acceleration of angle. As a result, we use 2 pi is also equal to 360 degrees. As a result, we have these three equations, 1, 2, 3, and we can get this new relationship of center acceleration omega r and v. And for the record, this is r omega squared because it is come from r over v squared, and v is equal to 2 pi r over t is equal to omega r. And then in this chapter we just have to combine the Newton's law with center acceleration, and we can write down by these two formula. F is equal to mass times acceleration, and then A, which is describe the center acceleration. As a result, center acceleration is a vector, and E is equal to R over V squared is equal to R over R omega squared. Yeah. And yeah. So we just have to combine these two formula in this chapter. Okay, let's see the example. In the example 1, a small ball of mass n is suspended from a string of length L. The ball revolves with constant speed v in the horizontal circle of radius r as shown in figure. Because the string sways on the surface of a cone, the system is known as a conical pendulum. Find an expression for v in terms of the geometry in figure. Okay. And in this example, we must think that what formula contains the term v, because we want to get a magnitude of v. So we must think of the formula of center acceleration equal to V squared over R. And then we just need to get the value of center acceleration in R, because V squared is equal to R times center acceleration, and then V is equal to R center acceleration. However, the small ball mass n is suspended from a string of length L, and its central force comes from the string's tension T. And if we draw the force diagram, it must have this is T, which can be divided in two parts. And this is NG. So we know the relationship between T and NG, which is T cosine theta. Why is T cosine theta? Because this line is perpendicular to the ground, and this is also perpendicular to the ground. Yeah. As a result, these two yellow line is parallel to each other, and then if we have theta here, then here is theta, and then T cosine theta is equal to NG. Then we know the value of the string tension is equal to NG over cosine theta. And the role of tension of string here is the central force. Then we know this part is T sine theta is equal to F, central force is equal to central force, and then E must be equal to N times central acceleration, right? Then we just need to do some substitution by T. T is NG over cosine theta. NG cosine theta times sine theta is equal to N times AC. AC is equal to maybe G tangent theta. And what is the value of R? This is the length of string L, and this is theta. As a result, our value of R is described here. The length of object to the center of the circular, which is L sine theta. Yeah. Okay. And then we just need to V equal to RAC equal to L sine theta G tangent theta. Okay. This is the answer of this example. And then we see example 2. A pack of mass 0.5 kilogram is attached to the end of a cord 1.5 meter long. And the pack moves in horizontal circular as shown in figure. If the cord can withstand a maximum tension of 50 newtons, what is the maximum speed at which the pack can move before the cord breaks? Assume the string remains horizontal during the motion. Okay, and in this example, we have to know the relationship between F and the speed. F speed here is V. What is the relationship between F and speed? Then we can say the F is the central force, right? They cause the central acceleration. Then the velocity can maybe we can use the velocity to describe the central acceleration, because if we have r, we can say the magnitude of central acceleration is equal to v squared over r. So what is the relationship of F and V? Is F is equal to F is equal to V squared. No, sorry. And V squared over R. Okay, so we just put the number in. The example assumes the string remains horizontal during the motion. As a result, the R is equal to 1.5 meter. And the pack is 0.5. And the maximum tension is 50 Newton. 50 Newton is equal to 0.5 times V squared over it's 1.5. And then V squared is equal to 50 times 1.5, 0.5 is equal to, and so V is equal to meter per second. Okay, so it's pretty easy, right? The next question is describe a 1,500 kilograms car moving on a flat horizontal road. Negotiate a curve as shown in figure. If the radius of the curve is 35 meters and the coefficient of steady friction between the tires and drive pavement is 0.523, find the maximum speed the car can have and still make the turn successfully. What is the still make the turn successfully? It means they keep the car on the road with radius 35 meters. Okay, and then we know that we must figure the relationship between center force Hc and the radius r. Okay, now r is equal to 35 meters. It will not change. And then what is the maximum speed v? As a result, we can write down the relationship between FC is equal to NAC is equal to NV squared over R. And what is FC? FC here is come from the friction force, which is mu s and normal force. And we can see the force diagram here. The normal force is equal to mg. And assume g here is 10 meters. Assume g here is this value. So we have the FC. So we can get the FC is equal to 0.523 times 1,500 times 10, which is equal to 1,500 times 35 over v squared. And then we can get a value of this. V squared is equal to 5.23 because here and times here times 35, and V is equal to 5.23 times 35. So basically we can get a concept of here. As R increase, the car can have larger velocity through the curve. Okay, and